So let's pick up where we left off with our discrete probability distribution. And if we're working with an expected value, that's a parameter for the whole population. So let's call it mu, because expected value is really an average, very much like the mean. I'm going to use the same symbol as we did for mean. And as I said on Friday, the mean describes a center, we should describe a spread. And then we can describe skew and other things as well. But we need to start with our idea of a spread, and that's a standard deviation. When we have a mu, we should find a variance in a standard deviation. I'm going to use the same symbol for standard deviation for sigma, and then variance sigma squared. So all we have to do to get from variance to standard deviation is take the square root. But the formula for this, we took each data value and subtracted it from the average, and then squared that. Well, how do I take the probability into account? I multiply each one by the probability of it occurring. And this measures our spread the same way it did for a general probability idea or for our tabular data back in chapter 3, where we described a histogram or a graph by how wide it was. Again, this is the variation from the average. Now, normally we would just count how many times that happened, but instead I'm going to multiply by the probability to do it. We had a probability distribution about people coming into the ER. And if I remember, I think this had an average that was like 2.25. Is that right? Is what we did on Friday? Okay. Then, to calculate the standard deviation, I have to add up 6 numbers. So when I start at x1, 0, I have 0 minus 2.25 squared times the probability of that happening. That's for this number. And then I do this number. 1 minus 2.25 quantity squared times 0.3. And then 2 minus 2.25 squared times its probability, 0.25. And then 3 minus 2.25 squared times 0.2. 4 minus 2.25 squared, 0.15. And 5 minus 2.25 squared times 0.05. The benefit of squaring is that it makes everything that we're adding here positive. But it also squares my stuff out. And my units don't quite make sense anymore. This would be in people squared. Yeah. So while the variance is a useful number, I find the standard deviation to be more useful, which means after I do this calculation, we take the square root of it. So multiply all this stuff out. Tell me what you get. A little bit of calculation later. What do you have?
1.6875.
Which is what I got as well. But again, as I said earlier, that numbers, units don't make sense. I think we'll be better served with the standard deviation. So since this is sigma squared, take the square root of that. And we get, let's only go say 4 decimal places here. That's in the right units. That's in people. So we expect 2¼ people, give or take. Oh, this is going to tell me the likelihood of being certain distances away. Now, every probability distribution is really governed by its mean, its standard deviation, and its overall shape, which we have yet to talk about. So my first reaction upon seeing this is, okay, I've got some function. In this case, the inputs are 0 through 5. You got those outputs. I've got this picture in my head of the probability distribution function. The bar chart, the column chart that we created using this PDF. I don't know what that shape is right at the moment. I could graph this one, I could find a shape, but given certain behaviors, given certain situations, some distributions are much more common than others. So it benefits us to talk about the main shapes we're going to use. But these are the two numbers that tell me about that shape. Where's the center of it? How does it spread? Questions on this calculation? Rarely will we have to do this whole calculation by hand. If we put this table into Excel and ask it to do the standard deviation of those top numbers with the weights, the distribution from the second row, it'll compute this automatically. Shape. There really are only two main shapes I want to talk about. The first one's called the uniform distribution. The best part about this one is that it's the one that you think of intuitively when you think of equally likely outcomes. So, if I ask you to roll a standard die, what are your possible outcomes? That's it. Now, assuming this is a fair die, what's the chance of getting a 3? Chance of getting any of these numbers? Right. Really, the probability of all of these is the same. It turns out that this type of distribution shows up a lot. In which case, I can calculate the mean and the standard deviation directly with my formulas, but I can do it easier in general. Let's take this same idea and change the die. Like I said, I got a lot of crazy looking dice here. Here's a die. Numbers from 1 to 20. But it doesn't even have to be a die. It could be, I'm going to go look at the weights of cars. Weights of cars happen to be uniformly distributed between 2,000 pounds and 5,000 pounds. So I go out and I look at a car, numbers somewhere between 2,000 and 5,000. In general, we're going to talk about a distribution from A to B, where A and B are just both numbers. So there's my list of outcomes going from A to B. Turns out, I know exactly how many numbers are in this list. If I asked you for the numbers from 1 to 150, how many numbers are there? Well, there's 150 of them, right? But how do I count them? Oh, and I want to say 150 minus 1, that would count all the numbers except 1. So I need to add 1 back on. If I want to count from 1,000 to 1,500, take 1,500 minus 1,000. But that takes away the 1,000. It's 500 numbers. So I have to add 1 back on. It's 501. Because I count both ends. As a matter of fact, this is true in general. From A to B is B minus A values plus 1. So if I'm going from 10 to 90, that's actually 81 values. I have to count 10 and I have to count 90. Think of it as actually making the bins in your histogram, right? We go from 10 to 19, 20 to 29, 30 to 39, 40 to 49, 50 to 59, 60 to 69, 70 to 79, 80 to 89. That's 80 numbers. Then I need 90 as well. So I get 1 more. This is often referred to as the fence post idea. If you want to make 5 sections of fence, you need 6 posts. Got 1 extra. But wait a minute. If that's how many values I have, then the probability of every one of them is the same. One out of. Which means with a little bit of algebra, I can add up all these numbers and I can find the mean. But I hope it makes sense for my expected value to be right in the middle between A and B. So I'm rolling my die. Numbers go from 1 to 6. What's the expectation when I roll this die? The expected value. Right. It's between 3 and 4. So I'd say 3 and 4. So I'd take the average of those, right? Exactly that idea. Again, with a little bit more work, I can compute the standard deviation directly. I've written it as the variance so that I didn't have to write a giant square root. But to get the standard deviation from the variance, all you would take a square root. I do not want you to memorize these formulas. These formulas appear at the bottom of page 202. I don't have these formulas memorized. I don't want you to memorize the formula. It's a pain in the neck. What I want to do is simply think about counting. Problem number 11 says the ages of programmers of a certain company are between 20 and 60 years old. What's the average age of a programmer? What's the expected age? Right in the middle, 40. I can compute the standard deviation. Right now, I'm not sure that's going to help me very much. So let me instead ask you a probability question. What is the chance when you ask a programmer their age that they are older than 40? Or equal to 40? Your first reaction might be it should be half of them, because 40 is in the middle. But 40 is a category. And so I'm including slightly more than half. Remember the fence post idea. I'm really asking for all of the ones from 40 to 60, because that is my upper limit, right? How many numbers are in this range? Aha, fence post issue. There are 21 numbers in there. 60 all the way down to 50 is 11 numbers. I got to keep the ones on both ends, right? So there's 21 numbers here. So there are actually 21 numbers. 40 to 60 is 21 numbers. So I'm asking you for the chance of 21 things. What's the chance of each of them? The probability of each of them. Oh, wait a minute. We wrote that up here. 1 over b minus a plus 1. So that's 1 over this bottom number. Now we're asking 21 numbers, each with a probability of 41. So the chance of getting a number bigger than or equal to 40 is 21 times 1 over 41, which is a little bit bigger than 50%. As a matter of fact, to 4 decimal places, that's 0.5122. There is in the textbook, again on page 202, there's a formula for the PDF and the CDF, but the PDF is uniform. Everyone has the same probability. That means if I were to graph this, every column would be the same height, wouldn't it? I can think of the picture of this probability distribution. It's starting at 20, going to 60, and every bar being the same height, 1/41. So I'm just counting up all the bars. What is the chance that I ask someone their age and they are younger than 30? Notice the inequality here. This is the same as asking them to be over 20 and less than or equal to 29. Because it says strictly less than 30. How many numbers are there? 10. There we go. This number is a little bit smaller than 25%. 24.39. 0.243. So when I'm dealing with a uniform distribution, every time I'm dealing with a uniform distribution, I don't bother to try and do this with formulas. There are a bunch of formulas on page 202 that I could use for the PDF, for the CDF even. I don't bother to draw this picture. I think that's easier than trying to memorize another formula, or even just to keep looking up another formula. Because you'll get a formula sheet for this next exam. You'll be able to copy all of those formulas off page 202 if you want. I just don't think they're useful at this point. Questions? There are two other examples on page 202 and 203 that I think are useful here. But this is not the one I end up using most often. There are a large number of mathematicians with the last name Bernoulli. There are 2 Johns, a Jacob, a Johann, and 2 Daniels. So the Bernoullis were a busy group of people. But Bernoulli thought about probability in a lot of places. And one of the things he worked at was the idea of doing the same experiment multiple times. We did this already. I said flip a coin 3 times in a row, right? The same thing happened over and over and over. But Bernoulli thought about 2 option cases. And really, I'm going to call them win and lose, or fail and succeed. We almost always code these as 0 and 1. So failure is a 0 and success is a 1. Now, this means that there's some special number, the chance of winning. When you do this thing once, there's a chance of success. Probability of success, or the probability of a 1. Our textbook, in a fit that absolutely pisses me off, says we're going to use P. But because this is a parameter, we're going to use the Greek letter P. Every time I see that, I think 3.14. And 3.14 is not a probability. So damn it, that bugs the hell out of me. Some books will just use the letter P, lowercase p, but we're thinking of this as the parameter for success on one experiment. With our coin, we were counting how many times the coin came up heads. And so the chance of success was 50%. It was either heads or tails. I could think of any other experiment that happens multiple times. For example, you have a driver's license. You had to go take a test for a driver's license, right? You had to pass the road test and you had to pass the written test. You couldn't take the road test until you passed the written test. So really it was the written test. Did you pass or not? What's the chance you pass your driving test on the first try? That's our probability of success. But you're not the only person who takes the driving test. The road test goes on all day long. A whole bunch of people take the driving test. How many driver's licenses are they going to give? Well, now it depends on how many times we do this experiment. And the thing about Bernoulli and binomial distributions is that it makes some assumptions. This number does not change. This parameter for success is the same every time. When you flip the coin, it's heads or tails 50% of the time. If winning means rolling this dice and getting a 1, that's always 1 in 6. So this parameter doesn't change, even if we do this more than once. Now, it turns out for one test, one trial of my experiment, and the one trial, it turns out the mean is exactly the same as this probability of success, because there are only 2 outcomes, and I multiply this number by 1, and I multiply 1 minus that times 0. This fail we coded as 0. So this is my average, my expected value. My variance is just the product of those 2 things. The idea that each trial is the same, that nothing changes. You roll this die, win is a 1, and the die stays the same every time. I should expect to win 1 in 6 tries. I have a variance 1 in 6 times 5 in 6. 5 out of 36. So I can compute these numbers directly. But I'm going to do this more than once. I'm not just going to do this once. These are referred to as Bernoulli trials. Like I said, for one trial. But if I'm doing multiple trials, Bernoulli trials Each one of them is independent, which means the probability stays the same. I'm going to ask to create a new probability distribution, like we did with our coin. I flipped it 3 times and I wanted to count the number of heads. Heads was a win, tails was a fail. That's a Bernoulli trial, and we got a very different looking picture. Rather than being the same 50% every time, we had a distribution that looked different. I'm going to let n represent the number of times I do the experiment. So instead of doing it once, I'm going to do it more than once. It turns out the best possible thing happens. Since each trial doesn't remember or care about what happened before it, every time I roll the die, it's a brand new thing. The expected value just multiplies. The variance just multiplies. And it turns out that there's a really nice formula that counts the number of ways we can do this sort of thing. I am now looking at a new probability distribution. The probability of getting R successes out of n trials. I flip the coin. What's the chance I get 0 heads or 1 head or 2 heads or 3 heads? Those were the options. We made that exact distribution on Friday. So, how do I count these? Well, it turns out that what I really need is a combination formula. Wait a minute. NCR. I did that before. That was unordered selection. That was a factorial formula, right? So I could have one success. I'm going to have 2 failures, but that one success could be the first coin or the second coin or the third coin to count all the options. Out of 3, choose 1 to be the success. The other 2 are the failures. Then I take the chance of success and multiply by the number of times we succeeded. And then I take the chance of failure and multiply by, raise to the power of the number of times we failed. Every single binomial distribution uses this formula. Now, I'm the first person to tell you this formula looks disgusting. Let me do a simple, quote unquote, simple example. Problem number 17 tells me we are going to run 9 trials. The chance of success is 90%. First question, what's the chance you get 5 successes? I don't know what this experiment is. Maybe it's the driver's license test. You know, there's a 90% chance the person passes the road test. We gave 9 road tests today. What's the chance 5 people passed? Well, what I need to do, probability, this is equal to 5, is 9C5 times 0.9 to the 5th times 1 minus 0.9 to the 9 minus 5 power. Now, I need you to go back to Wednesday to look up how to do 9C5. You can do it on your calculator. You can do it directly. There's a formula we had. If I remember correctly, NCR was n factorial over r factorial n minus r factorial. But we also had the C button on the calculator hiding under the math menu. Nine, and then I go math, PRB for probability. There's my NCR. 3, 9, NCR 5. So that number goes here. 0.9 to the 5th, 0.1 to the 4th. And literally, I type it exactly written that way. The chance that only five people passed their exam, if chance of succeeding is 90%, is 0.007. Why is that so small? What's my expected value here? Right, remember E of x is n pi, so in our case, the expected value is 9 times 0.9, 8.1. We're expecting way more people to pass, so the chance that only 5 pass is pretty low. Now, every time I do a calculation like this, I end up having to do this calculation over and over and over and over again. And that's really tedious. So I'm going to be the first person to tell you, I don't like doing these calculations over and over and over and over. So I'm not going to. In the back of our textbook is an appendix, Appendix A, and it says right there, binomial probabilities. There's a whole lot of stuff here. What the hell is going on? I need to know two numbers. I need to know how many times we're doing the experiment. I need to know the chance of success. The problem we just did had 9 trials. So I look for the number of trials until I find 9. 9. Now, this is way in the back of the book, and 9 actually spreads to the top of the next page. What I have next to 9 are a bunch of other numbers. What are those? Those are the numbers for how many successes I want. If I'm doing 9 trials, I could have no successes, 1, 2, all the way up to 9 successes, right? So I have 0 through 5 and then 6 through 9 on the next page. So here are all the possible successes. And then I say, what's our probability of success on one trial? What was our chance in that problem? 0.9. So I go to the column that says 0.9. 0.9, that's this column. Let me grab a mark so I can keep that column highlighted. There's our column. Please notice there are some dashes up here at the top. The chance of, with a 90% chance of success, the chance of getting no successes out of 9, 0 successes out of 9 trials is so small, it's smaller than 0.0001. So they didn't bother to write it down. It's a dash. Until I get to 3 trials, all of those are 0. 5 trials is 0.0074. Hey, look at that. That's exactly the number we came up with, isn't it? I don't have to do these calculations by hand. Somebody's done them for me. And this table in the back of the textbook allows me to do this quicker. We did 5 successes. And I said we were expecting 8 or 9 successes, right? Well, if I go down here and I look, 90% n is 9. Oh, 8 successes, 38.74%. 9 successes, 38.74%. This is a better way of getting the entire distribution without having to do the calculation by hand over and over and over. I don't want you to do this calculation by hand if you can at all avoid it. So that's why this little arrow is on my page here, because literally physically stuck to the edge of the page in my book, I put that little arrow so I could find it very quickly. I put the Post-it note in there, and in this case, Post-it note's a little metal arrow. And there's the entire table. Number of trials goes from 2 through to 16. There are a lot of possibilities back here. Chance of success goes from very small to very large. If I don't have the correct entry in my table, I can do this in Excel. So here is a blank Excel sheet. I want to do the binomial probability. So I'm going to write equals B-I-N-O. I'm going to write equals B-I-N-O. There it is, binomial distribution. That's exactly the thing I want, a binomial distribution. So I'm going to go click on this one, and then it says, hey, look, numbers, number S. How many did we do? How many trials did we do? So how many do I want to succeed? I wanted 5 successes out of 9. The probability of success was 0.9. Now, the last flag, the last thing here is either a 0 or a 1. In the words, it says cumulative. If I put a 0 there, it gives me the PDF. So it just gives me the chance of 5 successes. That's the same number we got, right? But if instead of putting a 0, I put a 1, it makes that the cumulative distribution. So that's the chance of less than or equal to 5. So it adds up all the numbers, 5 and 4 and 3 and 2 and 1 and 0. But it does it in one step. A bunch of those were blanks, right? They were really, really small numbers. So those numbers aren't that much different. But I don't have to do the PDF or the CDF by hand. Please, you need these tables. Put the mark in the back of the book, put it on your PDF version on our Canvas page. In the same module where the problem set data files are, you'll find a download version of the tables that's much more detailed than the one in the book. You can download all the tables from the back of the book as well in our Canvas page. We want to only have the 2 outcomes, success or failure. We only want to look at the chance of knowing how many successes. That's the important piece. You can flip the 2 and count how many failures. Just swap the N and the R. There are lots of other distributions. There's a Poisson distribution, again, named after a person. There's a triangular distribution. There are a whole bunch of other distributions, but I really don't think we're going to make all that much use of. But these ideas carry over from discrete behavior to continuous behavior. I really want to take these same ideas and stretch them into our continuous behavior as well. That's what we'll do starting on Wednesday. So technically, we didn't finish chapter 6 because I left out like 4 different sections in chapter 6, but this is all we're going to do in chapter. The homework for chapter 6 would normally be due 2 class periods from now. That's Friday. We're going to make it due Monday after break when you get back. So it's on the calendar for being due on Monday the 17th. We'll see you all on Wednesday, and we'll start talking about continuous distributions there.